So it's a pleasure for me to introduce our second speaker this morning, Thomas Nikolaus from Münster, and he's going to talk about polynomial functors and K-theory. We cannot hear you, Thomas. Maybe you should.
Yes,
Okay.
sorry, I can unmute myself. Yeah, thanks very much for having me, and thanks for putting together this conference in complicated times. And so, yeah, I'm talking about polynomial functors and K-theory, and this is joint work with Clark Barwick, Saul Glassman, and Akhil Matthew. And this is actually long overdue. So we've actually done that like 4 years ago. And I've already talked about it, but there were some aspects of it actually, which I might mention in the end, which we couldn't figure out since then. And now we put up the paper, one paper on the archive, and there will be another one, but somehow still there are some open questions in the end, which is the reason for that long delay. Anyways, but fortunately, Leonard has just talked about K-theory already. But let me still recall some aspects of K-theory. So R is going to be a ring throughout my talk. And let's recall that K not R, so the classical K group, was just done as follows. I take iso classes of the category proj R, by which I just mean finitely generated projective R modules. Projective R modules. So just denote the category proj R, and then I group complete that. And by group completion, I mean this is a monoid, these iso classes, by me not by a direct sum, and I'll group complete with respect to that. So in other words, the group completion is just a universal way of turning this monoid into a group, pretty much like the process which takes you from the natural numbers to the integers. So let me say that. So the map for any abelian monoid M, the map from M to M group is initial among maps into abelian groups. Maps into abelian groups. Sorry, I'm saying something everyone knows. So this means homomorphisms, additive maps from the group completion into any abelian group A is the same as homomorphisms from M into A, additive maps, right? That's the universal property of group completion. And that's what I do to this isomorphism classes of finitely generated projective modules. That's K naught of R. And I guess we see here immediately that, of course, this is not restricted to rings. As Leonard has already pointed out, I can easily apply that to additive categories and, if you want, even more general settings. And what I will talk about today is the structure that we have on K-theory. And let me start with K naught. So what is the structure on K naught R that we have in general? So of course, the first piece of structure is, well, it's an abelian group, so there's an addition. And let me maybe say that in a somewhat categorical way. So we have this map plus, which goes from proj R cross proj R to proj R with this functor. And this actually induced, like on iso classes, the monoid structure, which then after group completion led to the addition on this K naught R. Okay, so in general, K naught R is just an abelian group. But of course, if R is not just a ring, but R is commutative, then we have a second piece of structure on K naught R. And that is the multiplication. So in this case, we just have a tensor product. Right? If we have a commutative ring, we can tensor projective modules and get another projective module. So we have the tensor product, which is a functor from proj R cross proj R into proj R. Okay, and now the point is that this, in this case, induces the multiplication. K naught R cross K naught R. Oh, holy man, holy cow, just start erasing. Into K naught R. And how does that work? I mean, the point is this multiplication is defined by saying, well, if we have classes of modules, then this gets mapped to the tensor product. That's what I mean by it induces something. And then I guess you have to start thinking for 1 second what you do on like general classes, right? So after all, K0 was defined as a group completion. So a general class in K0 will be a difference, right? M minus M prime. And then you have to think for a second, what do I do on like formal differences of such classes? But then of course, you know, I mean, the multiplication is supposed to be bilinear. So you just multiply out what you get by the fact that multiplication is supposed to be bilinear, and then you get a unique expression, right, for formal differences. So say it differently, I want to turn K0 R and multiplication into a commutative ring. Right, and then the fact that, I mean, being a commutative ring means multiplication has to be bilinear, then this, together with saying what it does on actual classes of projective modules, determines what the map times on K-theory is. Okay, so that's the structure I think Lynette has already also talked about, the fact that K-theory itself is again a ring. And of course, I guess later in a second, we're going to talk about the K-theory space, and this is going to be a ring spectrum. But what I want to say now is the third piece of structure you get for K-theory of commutative rings, and these are lambda operations. So I do have another functor, which is lambda I, the exterior product functor. So this is a functor which takes a projective module to the i's exterior power of m, which is just a quotient. You take m to the tensor I, and then you apply a certain quotient, right? You anti-symmetrize the tensor. So, and in fact, actually you have to be a little bit careful. You also have to kill elements of the form m tensor m, right? I mean, if the characteristic is 2, then this might otherwise be non-zero. Okay, so this is what the exterior power is. And that's again a projective module. And the claim is that this also gives me a map lambda I from K0 R into K0 R. And of course, a map such that the class of a projective module is sent to the class of the i's exterior power of m. And here, actually, this is already a sort of non-trivial claim, because now maybe it's not so obvious what you would do with a class of a formal difference. Right, because I guess like for multiplication, it was easy. We just said it was supposed to be bilinear. But here, what are you going to do to a sort of class of a formal difference? And maybe in some sense, the talk today is about giving a systematic way of doing that, highly coherently. But let me first talk about the way this was classically done, and that was actually Grothendieck. So the following theorem, Grothendieck. So Grothendieck tells us that K0 R with these lambda i's, and I guess somehow maybe I should formulate the existence of the lambda i's as maps on K-theory is part of the result. And the result is that this is a lambda ring. And maybe let me say special in brackets lambda ring. So the point is in Grothendieck's times, what I'm going to list now would be called special lambda ring. And nowadays the terminology has slightly shifted and we just refer to that as a lambda ring. But what does that mean? So that is, we have equations of the following sort. So the lambda satisfies certain equations. And the first equation is actually that lambda n of b plus w. And this is an equation for arbitrary elements in K0 R, right? So the equation is that this is a direct sum, or the sum, sorry, I shouldn't say direct, it's just the sum, we're in a Boolean group, of I plus j equals n of lambda I v times lambda j w. That's the first equation. And I mean, this is actually how Grothendieck defines these lambda i's. Because if you think about it, so what you first observe is that if V and W are actually classes of projective modules, then this equation holds for the exterior power, right? This is just the standard property of how the exterior algebra transforms direct sums into tensor products. If you multiply that out, you get this equation. And then actually, you don't have any choice. If you want this to hold for all classes in K-theory, this tells you what you have to do to formal differences, right? Because if this equation is supposed to hold, you can you get an equation for what you want to have for what's the i's exterior power of this guy has to be. Is that clear? Okay, so anyways, that's the first equation. And then, but a lambda ring, and that's what makes it special, is has way more equations. And the second equation is I want to have an equation for V times W. And so the equation of a lambda ring is that there is some universal formula or polynomial in lambda I V and lambda J W for I J lesser equal N. So the claim is there exists a polynomial for every N, which is a polynomial in lambda I V and lambda J W, such that lambda N of V times W is this guy. And this is, I mean, the polynomial is most easily expressed in terms of elementary symmetric polynomials. Let me not do that. But the point is that this exists, and this is something which doesn't hold on the level of categories like the first one already. So this is already a K-theoretic, highly non-trivial claim. And the third point is that there's a similar formula for lambda n of lambda m of v. So that is again some polynomial expression, fixed polynomial expression in lambda I of v for, and I guess now I is lesser equal n plus n times m, I guess. Okay, so I guess that is what a lambda ring is. So, and again, they are actual polynomials. It's not that I just don't want to give them. There exists a polynomial, and a lambda ring is the structure of a commutative ring together with operations lambda I, such that they satisfy these equations. And this is already for K0 of a ring. This is actually a sort of highly non-trivial claim. This is not an easy theorem. I mean, I guess Grothendieck proves this using some sort of splitting principle. But if you just try to write it down from properties lambda I has, this is close to impossible, even though it sounds very innocent. On the other hand, these lambda operations have, I mean, there's important consequences of the existence of these lambda operations. So they give you very important pieces of structure in K-theory. For example, Quillen shows that you can sort of reduce the vanishing of the p-adic higher K-theory of perfect fields, the characteristic P from that, and so on and so forth. Okay, so, and I guess what is the talk today about? So I want to talk about the following questions. So the first question is, do the lambda I, which are mapped from K0 R to K0 R, and these maps are not additive, right? We just had a formula for what they do to some, so they are not group homomorphisms or anything. They're just maps of sets. And the question is, do the lambda I lift to maps of spaces? KR to KR, where KR is the K-theory space, where KR is the K-theory space. And I'm not saying spectrum here because they will not be additive maps. So there's no way these are going to be maps of spectra, but they could be maps of spaces. And of course, I mean, I'll comment on that later, but I mean, the answer to this question is of course yes. And this is classically known by work of Quillen, Grayson, Hiller, Kretzer, and others. But maybe I want to present a way of thinking about that, which is a little bit more along the lines of functoriality, that in the highly structured sense. But I guess this, so this is related to if so if yes, and the answer will be yes, what is the structure, the operations lambda I encode on KR, the K-theory space. So right, so somehow on K0, on the set K0, they encoded the structure of a special of a lambda ring. That's what Grothendieck theorem is. And I want to ask the similar but higher algebra version of that question. What is the highly coherent structure that these operations encode on the K-theory space? And this is maybe actually, you know, the motivation for this work. This was a question, I think, raised by several people. But yeah, I'll come to that in the end if time allows. But maybe another version of question one. So for question one, somehow I asked the question about the exterior power functor, but there are other functors like Schur functors. And the question is, what about other functors? Like, I guess, for example, any functor which has the form V goes to the n-fold tensor product V, and maybe you could sort of just take a quotient by a symmetric group with some symmetric group module M, like Schur functors. Like, do they also induce maps on K-theory? And when does that? How do I know that a functor induces the map on K-theory? That is maybe the main question I want to talk about. Okay, so that was the motivation and questions for my talk today. Good. So are there questions about this part? Otherwise, I would go on and talk about how to answer this question and maybe present a systematic way of doing that. And the systematic way is involving polynomial maps and polynomial functors. And so let's take a step back and talk about what polynomial maps are. So the setup I want to go into is A is an abelian group, and M is an abelian monoid. I mean, if you want, just think of M also as being an abelian group, but it will come convenient to allow this generality. And what I want to define is what polynomial maps are. So I want to define when a map F M to A is polynomial. Well, maybe I should say polynomial. And polynomial always comes with a degree, pretty much like, you know, from ordinary algebra. A polynomial is always a polynomial of some degree. So I say polynomial of degree -1 if it is trivial. So just a zero map. There's exactly one polynomial map of degree -1, and that's a zero map. And of course, this is boring, but I just do that to start an inductive definition. And then it is polynomial of degree lesser equal n plus 1. Maybe I can make it yellow. It looks a little better. Okay, so that's the definition. Polynomial of degree lesser equal n plus 1 if for each y in M, the map dy f, which goes from M to A and which sends x to f of x plus y minus f of x, is polynomial of degree lesser equal n. Okay, so that's the definition of being polynomial, map between Billion groups, or say from a monoid to a Billion group. Okay, and I guess, well, let's make one example. For those of you who haven't seen that definition, this, I mean, looks a little bit confusing at the beginning. Well, let's first work out what polynomial, and of course, I should maybe have said this. In general, I just call a map polynomial if it's polynomial of some degree, some finite degree. And so I guess, what does it mean to be polynomial of degree? Polynomial of degree less or equal 0. Well, let's just investigate the definition. So I guess this just means that for every y, the map fx plus y minus fx has to be polynomial of degree -1, which is the 0 map. So in other words, for every y, fx plus y has to be equal to fx. Well, that just means it's a constant map. Right, and then I guess you can start sort of going up the ladder to see what polynomial in the next degrees will mean. So in the next degree, you'll find something like affine linear. And I think it's a great exercise to work out what polynomial maps from Q to Q are. And the claim is that these are exactly just polynomials in the classical sense. So polynomial map from Q to Q, polynomial map of groups is just exactly given by a classical polynomial. And so this is maybe I leave as an exercise, which is really instructive in order to understand the definition. And maybe this is not completely easy. So maybe you want to first, if you know what the cross effect is, first redefine the definition in terms of cross effects to have a chance of getting at this exercise. Okay, and then similarly, you can check out what polynomial maps from Q to the n into Q are. And this will just be like polynomials in several variables, in n variables, right? In an obvious way, a polynomial in n variables gives you a map from Q to the n to Q. And that is what polynomial maps are. But then you have to be very careful, actually. If you work with these cross effects, you'll see in order to get that, you have to divide by something like n factorial to translate the nth part to the nth cross effect. And so, for example, you could ask, what are polynomial maps from Z to Z? And this is a little bit more interesting. So here you see that this is actually given by, well, you can just take a polynomial map of Q, X, right? So this gives me a map from Q to Q, and you just require that it sends P, the integers to the integers. Right, because being polynomial was something that was intrinsically characterized. If I have something from Q to Q, which I know is polynomial, and takes the integers to the integers, then it also has to be polynomial, the map from Z to Z. And it turns out there are polynomials with non-integer coefficients, which have the property that they send the integers to the integers. For example, binomial coefficients. And in fact, it turns out that binomial coefficients form a basis of those. So what you can do is you can write every such polynomial map as a linear combination of polynomials of the form x over I. So maybe that's a polynomial in x with integer coefficients alpha I and z. So all polynomials with this property take this form. Okay, so you see, there's this notion of polynomial maps, and it roughly recovers what we mean by polynomials, but you have to be a little bit careful as it's intrinsically characterized. Okay, so that's a classical notion, and the point is that, of course, it turns out that, I mean, the composite of polynomial maps is again polynomial. It's also something you have to check, and the degrees behave the way you would expect that from composing classical polynomials. And the amazing fact is the following theorem. which is a little bit hard to track actually in the literature. Maybe a version of that can be found by Dold, then maybe Parsi has something related to that, and then Lukowitsky, maybe some others that I'm forgetting. And the theorem is the following, that initially when we talked about group completion of abelian monoids, I said this has a universal property that additive maps out of the group completion are the same as additive maps out of our initial monoid. And the cool thing is that this is still true for polynomial maps. So the induced map from polynomial maps, so M is going to be a abelian monoid into any abelian group. So M is a monoid, everything abelian, A is a group, abelian group. So you have this, and then you can go back to polynomial maps M into A, and the claim is a bijection. Sorry, this is maybe hardly readable, admittedly. Is a bijection. So in other words, and I still find this very surprising. So in other words, the group completion is not only universal for additive maps, but actually for polynomial maps. Right? It has a universal property in the land of polynomial maps. And yeah, this is a theorem. And I guess the proof, I mean, let me maybe not comment too much. Maybe let me give you 2 lines of, the one needs to prove that. So the idea is to say that polynomial maps Hom poly from M to A are actually the same as Hom's additive maps from some group ring modulo I to the n plus 1 into A. The polynomial degree n maps are the same as maps out of some group ring where I is the augmentation ideal in the group ring. And so this is kind of what Parsi shows and what is not. I mean, what is basically an unfolding of the definition. But once you know that, you just have to compare, you have to check that the group ring M modulo the augmentation ideal, the n plus first power of the augmentation ideal is the same as the M group I n plus 1. And the latter is the right-hand side is obviously a localization of the left-hand side, and you just need to check that the elements at which you localize are already units in the left-hand side. That is the idea here. But yeah, this is not a really hard proof once you translate everything correctly, but I still find the fact that this is true very stunning. Fact that the group completion has more universal property than you would a priori expect, or that it has by definition. Okay, and so I guess this indicates that K0 should have more functoriality than you'd a priori think, right? Because it already tells you that if you think K0 is a group completion, it will somehow be functorial in polynomial maps. And now maybe the question is, which functors between categories induce polynomial maps on isoclasses of projective modules? Right? Because if we have a functor between additive categories, which induces a polynomial map on isoclasses of projective modules, then it will, by what I just said, induce the map on K-theory. And that lets me to climb up the categorical ladder by 1 to talk about polynomial functors. And that is something which has been studied classically by Eilenberg-MacLean. And that is if C and D are additive categories, and I want D to be idempotent complete. So this is not exactly necessary. You can always embed any D into its idempotent completion. So then you can define that for arbitrary D. But let me do it like that. Then I say that a functor f from C to D is polynomial. Well, I guess now I'm going to do the same, the categorification of the definition I had before of degree -1. I want to make it yellow. Of degree -1 if it is trivial. So by trivial, I just mean it's a zero functor. And it is polynomial of degree less or equal n+1 if for every C in C, or let's say Y in C, the functor dyf, which is a functor from C to D as well, and it sends x to f of x plus y minus f of x. Let me write it like this. So what this means is f of x is canonically a summand in f of x plus y, right? Because on the level of additive categories, we have the inclusion from x into x plus y and the projection from x plus y to x. And because I'm idempotent complete, I can canonically split off the other summand. And that's what I mean, yeah. The notation I learned from my student Felix, this minus. Anyway, so that's a direct minus operation. So that's what I mean here. And so the claim is that this functor is polynomial of degree less or equal n. Okay, so that is what I have here. That's a definition of polynomial functors. I mean, there's a bunch of equivalent definitions, and usually you maybe see a definition in terms of cross effects. Let me give you one warning. This is not the same or not related, say, I mean, it's probably related in some ways, but not the same as the notion of polynomial functors from logic computer theory. So the one where you say it's a pull-push operation corresponding to a span. And yeah, it's a different notion. I guess I discussed that with Joachim Koch a little bit over the last days. So it's not so easy to say how the two notions are related. I think they're just both incarnations of generalizing the concept of polynomials, and maybe both in different ways. Anyway, so here's examples. So there is this functor proch r to proch r that we've talked about the whole time, which is sending m to the i's exterior power of m. And that is a degree I functor. So this is actually a polynomial functor of degree I, as one can figure out. And yeah, so this is, by the way, related to the binomial coefficient functor, if you think about it. Because if you think about what it does on a basis, then it will send it to, I mean, like subsets of that basis of a fixed cardinality. So that's basically the higher algebra, or the categorical version of the binomial coefficient functor, n over I, I guess, x over I. Okay, so that's an example of a polynomial functor. And again, this is not entirely easy. I mean, you have to sort of understand the definition to see that this is actually a polynomial degree I functor. And also these kind of sure functors, like for example, the symmetric power functor would be an example. Okay, so that's a polynomial functor. And again, we have that polynomial functors are closed under composition. So composition of polynomial functors is polynomial. So we have a category. And actually it's a two category of polynomial functors, which I denote cut additive and put poly to indicate take polynomial functors, and of course we have a functor. So this is, maybe I write this, additive categories, cats and polynomial functors. And here I have also the category of additive categories and additive functors. Additive cats and additive functors. And of course, there's a functor like this. Oh, shit. Sorry for swearing. So there's a functor like this, which takes, I mean, of course, an additive functor is a special case of a polynomial functor. It's a polynomial functor of degree 1. Okay, good. So that is the setup. And I guess now with this notation, we can draw an immediate corollary from the theorem about group completion being universal for polynomial functors. That's the following, namely it says K0 is functorial in polynomial functors. Sorry, I should write functorial and not functor. Functorial in polynomial functors. What does this mean? So I guess this means we can look at the category of additive categories and additive functors. And so by definition, K0 was a functor from here to building groups. And we can just forget and consider it as a functor with values in sets. And then we have these larger categories where we have additive categories and polynomial functors. And the statement is that this canonically extends to a functor here. And if one says it correctly, it's even unique. So there is an extension. And that is why stuff like lambda I just, the claim, this means lambda I, that there's always a way to sort of extend lambda I to K0, for example. And the proof is now easy. So what you check is just if f from C to D is a polynomial functor, you just check that the composition from iso classes in C to iso classes in D, F, and then down to K0 in D, that this composition is polynomial, and then from the universal property of K0 C, it extends like this. Right, and that is the induced map on the group completion. And that is the induced map on K-theory, and then you check easily that this whole thing is actually functorial. Okay, so that is a systematic way of getting the fact that K-theory, I mean, you can apply K-theory to polynomial functors and not just additive functors. And now, now I can state the main theorem that we prove. Theorem. Oh no. And that the same thing is true for K-theory as a functor with values in spaces. So the K-theory space is functorial in polynomial functors. i.e., we again have an extension. We have the category of additive categories and additive maps. And then I guess I haven't really talked about the K-theory space, but I guess Leonard has. So we have K-theory as a functor on that, and I guess really it lands in spectra. But again, pretty much to, as I did before, when I'm forgetting from Abelian groups to sets, I forget from spectra to spaces. Maybe I write spaces. So that's the infinity category of spaces, aka homotopy types, aka anima. And here I have cut at poly. And the theorem is that there is again an extension, K tilde here. So in other words, the K-theory space is polynomial and functorial in polynomial functors. Okay, that's the main theorem. And let me immediately make a bunch of remarks. And the first remark is, maybe let me first explain the K0 version of this remark. So you might think that, well, you know, if I forget the fact that K theory is an abelian group, I have forgotten something, right? I have forgotten the abelian group structure. So if I just knew that K theory was a functor on additive categories and polynomial maps, it can only land in Z. And you might think, well, this functor has somehow forgotten the abelian group structure, but it has not. And the reason is that, of course, the direct sum, for every additive category, the direct sum is polynomial. So once you know that K theory is polynomial, and actually you also know that it preserves products, you get immediately that Ka, you get an induced map Ka to Ka. Or I guess 0 if I talked in ordinary land. And then this will recover the abelian group structure on the set K0 of A, or respectively the space K0 of A. So in the space version, this means Ka is a connective spectrum. So what I'm saying is that just from knowing it's functorial and polynomial functors, you immediately recover the fact that it's in fact a connective spectrum and not just a space. But of course, you recover more. You also, like, if for example, R is commutative, we also have this functor tensor R from proch R to proch R, and this then actually gives us that KR is an E infinity ring spectrum. Again, because this functor is polynomial as a functor of additive categories. And the next remark I want to make is, well, we actually prove something stronger. Namely, we prove the same version for stable infinity categories. Lennart has mentioned in his talk that K theory really can be considered as a functor on stable infinity categories and not just additive categories. So what one has is the category of small stable infinity categories and exact functors. And so K theory naturally can be considered as a functor from here into spaces. And then it turns out there's also a notion of polynomial functor for stable infinity categories. Poly. And that is has been invented by Goodwillie. So this is just what is called a functor is n-excisive for some n. Right? Polynomial of degree n for additive categories corresponds to the notion of being n-excisive for stable infinity categories. And so what we really prove is that K theory in this generality extends to this. And the old theorem we have up here about additive categories is a special case, because for every additive category you have a stable envelope functor, some other derived category of that additive category, if you want to say it in classical language. And then any polynomial functor in the sense of Eilenberg-MacLane on an additive category induces an n-excisive functor on the stable envelope. That's, I guess we proved that in the paper, but this is somehow well known. And so as a result, you can just embed, so to say, or have a functor from additive categories and polynomial functors to stable infinity categories and polynomial functor. And the point is K theory doesn't change under this maneuver. Placing an additive category by its stable envelope does not change K theory. Okay, so that is the main result. And actually, I should say that this also gives us, oh, is there a question maybe? Oh, is there a more structured object than Z, but less than up that cut poly projects through? Well, I guess, yes, the answer is yes. And this is maybe abelian groups and polynomial maps, right? So by the methods I did. So you could just replace the target by abelian groups and polynomial maps. And I can say one sentence about non-connective K theory, but this is going to be a little tricky. Oh, Right, so I guess now I can come back to my exterior power functor. That's the following example. And that's, I mean, there is this functor lambda I from proj R to proj R. And of course, now that we know that polynomial maps induce maps on the K-theory space, we immediately, just by functoriality, get a map KR to KR, map of spaces. And I should say, really, this was, I mean, this was known. Such maps in this specific case had been produced way, I mean, back in the day when K-theory was introduced. Quillen already produced such maps, and then I guess a lot of people produced versions of that. Maybe Hiller, Kratzer, Grayson. I mean, there's a lot of accounts of such maps. But the point is, the way they usually do that is by means of sort of adhering to some computation of K-theory and some plus construction version. So in the end, what they produce is at most somehow these maps up to homotopy, or probably even up to phantoms in some sense. So the main point of what we do is to not just produce these maps one at a time, but to produce this coherently as a functor. Right, so having a functor and the functoriality, especially in this kind of higher categorical incarnation, is much more useful than just saying for every map I have a map. But I should mention that the sheer existence of this map was, of course, known long ago. And so I guess this is just me saying that functoriality is the point. And so the functoriality has a number of consequences. Right, this is about higher structured version of relations between functors and connectivity. And maybe the first thing is whatever structure the category proj R or versions of it with have will also gives the same structure on K of R, as long as the structure is incarnated through polynomial functors. So for example, I mean, there's this kind of way of saying that, I guess, well, what's the best way of saying that? I mean, there's this fact that you can look at the category, the functor, look at the functor G mod H. So for a finite group G, or actually a profinite group more generally, you can look at the functor which sends an orbit G mod H to the category of representations of H on R. So this is the category of H representations on finitely on proj R, i.e. a functor category from BH to proj R, right? It's not the same as a projective module over the group ring. It's a module over the group ring, but which is underlying projective. And then, I mean, the claim is that this extends to what is called maybe a G symmetric monoidal infinity category. Monoidal infinity category, i.e., and I guess there's a very beautiful incarnation of what this exactly means in the work of Rune Haugseng and Eldon Elmanto. I think Rune will talk about this exact work tomorrow, i.e. by work of Haugseng Elmanto. Well, I guess Elmanto Haugseng, sorry, don't know the alphabet. I guess, anyway, so we have, this is it's what is called a G Tambara functor, or at least their incarnation of a G Tambara functor in cut additive poly. i.e. functor from bispan category. I think Rune will talk about this. Fg into cut additive poly. And thus we get that K-theory, KGR, which is just the K-theory of this representation category. Rep RG is a G Tambara functor. So this is just, it's just a fancy version of saying that, there's additive transfers and multiplicative transfers related to induction and restriction of representations and tensor induction of representations. And those functors combine together to give a highly structured statement on the level of categories. And all these functors are polynomial. So we can just hit it with K-theory, and then we get the exact same structure on the K-theory space. And that will actually give us highly structured versions of equivariant K-theory, equivariant algebraic K-theory, which is even fancy multiplicative. Okay, that was an example for people who like equivariant homotopy theory. But let me give you the example which motivated us, and that is this lambda ring. So let me maybe first give you a zoomed out version of the result. This is that there is a version of, or like a higher homotopy coherent higher version of a lambda ring, which is a space together with maps lambda I from that space. Maybe let's call that space, what's a good name? A to A, plus A to A, sorry, I guess plus takes two inputs. And tensor A to A, satisfying higher coherent versions of the lambda ring laws. And actually it will, this will be incarnated by an algebraic theory. It's a model for a certain Lavier algebraic theory. A model for a certain Lavier algebraic theory, or rather the infinity version of a Lavier algebraic theory. And the point is that for R a commutative ring, we prove the theorem that K-theory of R has this structure. And this is rather a consequence of our polynomial functoriality, because what the idea is, you just sort of assemble together all the exterior powers and tensor products and sums on the level of categories. Just check out what kind of coherences you have there, and then you hit it with K-theory again. And that will produce for you just by functoriality the exact same structure on the K-theory space. Right, and for this is actually very crucial that you have actually that K-theory is functorial in a highly coherent sense on polynomial functors, and not just as up to homotopy or up to phantoms. And let me give you, like, as a last statement, one concrete corollary of that, which I think is a new result, is that if R is an FP algebra, then what you can do is you can look at K-theory of R, and then you P-complete it. Well, that's just my notation for the P-completion of algebraic K-theory. And the statement is that this is naturally an animated ring, aka simplicial commutative ring. So in particular, so a priori, this is an E-infinity ring for arbitrary rings, but here the statement is this admits the structure of an animated ring. E.g., it admits the homotopy groups, e.g., the homotopy groups K star, RZP admit divided powers. Canonically, functorially. And this is, I think, a new result. I was not aware of structure. And I think the statement is that, I mean, this is closely related to Milnor K-theory, because if you think about what these divided power structures will do, and you think about the comparison with Milnor K-theory, see that you'll have that somehow. I mean, I guess Milnor K-theory basically is generated under those from degree 1 elements in some sense. Okay, so maybe there was a question in the chat before I go on and say things a little bit more systematically about spectral lambda rings. Jonathan asks whether we can derive a polynomial functor approach R to a polynomial functor dr. Yes, I think so. What you do is you just extend it to the stable envelope, and then, I mean, take int, I guess, yes. Right. Oh, an animated ring. And so I guess Hinich asked what an animated ring is. An animated ring is just a new word for simplicial commutative ring. Commutative ring. And this is, I mean, you see, the point is that a simplicial commutative ring is something which is more than just saying an E-infinity ring. So a simplicial commutative ring is a stricter structure than an E-infinity ring spectrum, if you know that. So, I mean, for one, it's a module over the Eilenberg-MacLane spectrum, but it's even more than that. For example, on homotopy groups, you have, or like, I mean, say maybe say it differently. It's a model for the algebraic theory of polynomial rings. But a model in the land of spaces. So the ordinary one categorical theory of polynomial rings you consider as an infinity Lavier theory, and then it's a model for that. Okay, so, and good. Are there further questions about this part of the talk? Okay, so let me end by roughly sketching how we set up this theory of spectral lambda rings. And this is actually not so complicated. This just goes back to something about, I guess, to the definition of strict polynomial functor. But a strict polynomial functor, and I guess I want to look at strict polynomial functor from Proch n Cartesian products of Proch C to Proch Cm is a scheme, maybe scheme enriched, that's one way of saying it, enriched polynomial functor. Equivalently, for every, or like, I mean, said differently, it's a map of stacks from the stack of vector bundles to the n to the stack of vector bundles to the m, if you consider those as stacks on the category of commutative rings. So in other words, for every commutative ring R, a polynomial functor Proch, well, let's call it FR, from Proch R to the n to Proch R to the m, and that base change. i.e., we have that FR to the tensor RS. So if we base change up, that this is the same as FR tensor S maps. Yeah, for R maps to S. So in other words, those polynomial functors which just act on all categories of projective modules for all commutative rings. Just a universal polynomial functor, if you want to say it like that. Right, and this is, I mean, this definition is due to Friedlander and Suslin. Right, these are somehow the, I mean, there can be, for a specific commutative ring, there can be a lot of polynomial functors from Proch R to Proch R, just taking into account the specific structure of that commutative ring R. And the strict polynomial functors are the ones which somehow exist for every commutative ring, the universally existing ones. And an example is, of course, the exterior powers. symmetric powers, and so on. Those functors that exist for all rings. And then, I mean, using that, we can just define our spectral lambda rings as follows. That's just saying that we define an algebraic theory, an algebraic Lavier theory, or like an infinity version of that, as follows. We could just call it TFS for Friedlander-Suslin. And it's just that the objects are, I guess, like in an algebraic theory, the objects are just always the natural numbers. But I guess I want to think of the natural number n as just broad z to the n. And then the morphisms are just sort of, I guess I want to say strict polynomial functors. Strict polynomial functors from proj r to the n to proj r to the m. But what I want to do is I want to apply K-theory to that category. Well, the category of strict polynomial functors itself is somehow a category of which I can take K-theory. This is, I guess, I mean, it's an exact category. You have to be a little bit careful. You can't, I mean, as Leonard pointed out, you can't quite take group completion K-theory here, but you have to take the exact K-theory, or maybe a better way of saying that would be to do everything derived right away, and then it's K-theory of stable infinity category. Okay, so then, I mean, this is the first part, and then the second part is, and then.
Sorry, Thomas.
Yes.
I can't quite read what you wrote under objects.
Objects are proj z to the n. Or morphisms, sorry.
Yeah, sorry, what are the morphisms? I guess I just can't read what you wrote there.
Okay, so sorry, man. My handwriting is degenerating. It's like several months of lockdown and I can't write anymore, sorry. Morphisms, I mean, not that I ever could write cleanly. Okay, so morphisms are just, you take the category of strict polynomial functors. And I again managed to write too far to the right, so maybe I write it here. Take the category of strict polynomial functors from proj z to the n to proj z to the m, right? That's the category. So we look at strict polynomial functors, and then you want to apply K-theory to that. So that's a space. Right? Is that okay, Jay?
Yeah.
Okay. Good. So, and again, this is a space. So of course, this is going to be an infinity algebraic theory. And then using this, I just define that a spectral lambda ring is just a product preserving functor. Product preserving functor. Functor from this algebraic theory to spaces. In other words, a model for this algebraic theory. And you see, I guess the point is the following, and then this is maybe a theorem, which hasn't yet appeared in what we have written uploaded yesterday, but that is that I guess the first statement is for every spectral lambda ring A, which is a space with additional operations, we have the first statement is that pi naught A is a classical lambda ring. So this is actually already quite something, because as I said, it's not even in the case of ordinary K-theory so easy to verify these universal polynomial equations that Grothendieck has shown to hold for ordinary lambda rings or K-theory of a ring. And secondly, I guess A has an underlying, there is an underlying E infinity KZ algebra spectrum, and the functor from E infinity, I mean, spectral lambda rings sorry, I should write like this is forgetful functor to E infinity KZ algebras is monadic and comonadic. So this is what is called pleasure sometimes. So if you think about, I mean, in other words, it has a left and a right adjoint, and somehow we can say something about left and right adjoints. The right adjoint is a version, I mean, it's a specific spectral version of Witt vectors, if you know what that is. And the left adjoint is some sort of spectral version of the algebra of symmetric polynomials. And maybe the most important part is that for R, an ordinary commutative ring, we have that K of R is such a spectral lambda ring. And the second part is actually easy because why is the second part easy? That's just because let's look back what this algebraic theory was. This was essentially constructed from strict polynomial functors. And by definition, strict polynomial functors act on projective modules for every commutative ring R, right? And they act through polynomial functors. So just by functoriality, they will also act on K-theory. And so the K-theory of those strict polynomial functors also acts. So basically, given the definition, the part 2 is just an incarnation of the polynomial functoriality. And I maybe should end my talk with that. I could go on and talk about these spectral lambda rings for quite a while. The problem is, I guess the way I've defined it was just a universal definition. You know, that's a kind of style of math where you put everything complicated in the definition, and then somehow theorems are easy. So here, once I know that K-theory is polynomial functorial, I could just say, well, the structure I have on K-theory is exactly the structure that the category has through polynomial functors. I've just made this into a definition. So the key part here with this last theorem is that actually one can compute what the K-theory of these categories of strict polynomial functors is. And that is because, I mean, this is something very classical studied in representation theory. I think Krause and others have studied that. So you can decompose these strict polynomial functors. And so the point is the K-theory is basically generated by these Schur functors. So the K-theory is basically generated by the exterior powers, if you say this correctly. And that's kind of why this really captures the notion of a lambda ring. And so that's one thing I wanted to say. And second thing I wanted to say is that, of course, you could imagine a more general theorem where not only the category of projective modules for an arbitrary ring is, but you could wonder, like, what exact structure do I need on the category, on a category, say a stable infinity category, so that its K-theory is a spectral lambda ring. And that structure is what will be subject to future work of some PhD students from Northwestern, namely Grigory Kondriev, Kirill Magidson. Oh, sorry, my handwriting completely degenerates now. Wait, what's going on here? My pen is running out of battery. Sorry for that. And Artem Pridoko. So they set up a notion of symmetric monoidal category. Monoidal category that has an action of the strict polynomial functors, or rather an infinity version of that strict polynomial functors. Sorry. And then combined with our work, this implies that K-theory of such a category C is a spectral lambda ring. Right, and again, I just want to highlight this is not an easy result, because these universal polynomials that come up in work of Grothendieck, they contain minus signs and so on and so forth. So you can't really expect that to hold on the level of categories, some version of these universal polynomials. So the key is to actually somehow have an action of all polynomial functors and all relations between those to get the induced structure. Okay, so I think I want to end my talk here. So the punchline is just that once you have polynomial functoriality for K-theory, you just can sort of get structures on K-theory from structures on the category in a very universal and sort of easy way. Okay, thank you very much for listening.
Thank you very much for your talk, Thomas. So are there any questions or comments?
Would another punchline be that K-theory is a Schur functor?
Right, so I'm not sure what you mean by a Schur functor.
Like SCHUR, it projects onto groups or the category of groups or abelian groups in the way that Schur functors do in other spaces.
Well, I'm not entirely sure I know enough about Schur functors to fully understand what you mean by do in other spaces.
Okay.
Sorry, I guess, certainly one punchline would be to say these kind of, I don't know. I think I just don't know enough about the way you think about Schur functors on different spaces to say yes or no. Probably yes.
I have a question about this this equivalent stuff you mentioned earlier,
Right.
where you were looking at this Kg of R defined as the K-theory of fun BG proj R.
Yeah.
And how does that relate to fun BG perf R, the K-theory of fun BG perf R?
You mean like, sorry, I'm not sure which bracketing you mean. You mean BG perf R upper, sorry, BG D R perf or something outside?
No, inside.
No, I want to, oh yeah, that's equivalent.
Okay.
At least, well, I guess, wait, do I know that this is equivalent? I want it to be. So to be honest, I guess I usually would take fun. Yeah, I guess I maybe have to admit that I don't know that the two are equivalent. I would. So I guess I usually take this thing that you mentioned. And I guess what's one and people would classically do would more be like, right, fun BG into proj R and then maybe the stable envelope of that.
Okay.
And I guess I'm not general. I think I don't know that the two are equivalent. This question, I thought about this question a couple of times. The problem is, I guess you can't quite get a
filtration, right?
You can't quite get a weight structure. So yeah, I think, to be completely honest, I almost all of the time work with this upper guy.
Okay.
For the sake of this talk, because I talked about additive categories and proj R, I wanted to say it like a little bit more down to earth.
Okay.
But in the end, the result of Hauxer and Elmanto tells us that both are somehow G Tambara functors, and maybe they're not the same. Good point. Thanks for.
Okay, thank you.
Thomas, can you say a little bit more how you get the structure of an animated ring on the P-complete K-theory of FP algebra?
Yes. So, so it turns out that, okay, so I guess you have to, this is a computation, you compute that. I guess, let me say something more generally, I say that K of a commutative ring, R is a commutative ring. I say if you base change this over Kz to the bottom cell of Kz, the integers, this is an animated ring. And so it turns out, for FP algebra, you just base change along KFP basically. And KFP p-adically is just an Einberg-MacLane spectrum. That's how some of the two results relate. And so what you get is actually a priori, this is actually an animated ring. And so this is implied by saying, so I claim this is implied by saying that KR and so KZ, Z is a spectral lambda ring over Z. And right, so I know that, I guess I want to talk about this implication now, but what our results first tell you is that this is a spectral lambda ring over Z. So a priori, K-theory is a spectral lambda ring over KZ, and then you base change it to the integer, so it's a spectral lambda ring over Z. And then you have to understand what a spectral lambda ring over Z is. And so I guess this, I mean, for this you have to compute what the K-theory of strict polynomial functors is. Right? It's a model of an algebraic theory. You have to understand this algebraic theory. And the claim is, for example, that the K-theory of strict polynomial functors from, oh, sorry, not poly, Proj C to Proj C. Proj C is actually the following. So let me maybe say what the homotopy groups are. So this is actually K-theory of the integers. And then you adjoin S1, S2, S3, and so on. And the Si are the elementary symmetric polynomials. Symmetric polynomials. Concentrated in degree 0. So in other words, this is just on homotopy groups, it's actually the free lambda ring on a single generator over Kz on homotopy groups, right? So the sort of algebra of symmetric polynomials. And so as a result, the base change, so if I base change to K of to Z, so along Kz to Z, this is just actually the ordinary category of the ordinary algebraic theory of lambda rings. So say it differently. So what I'm getting at is that if I take this Friedlander-Suslin theory of strict polynomial functors and I sort of base change it over Kz to Z. So you have to think a little bit what I exactly mean by that, but basically you just apply the space change to all the mapping spaces in question. And this is the ordinary theory of lambda rings over Z. And so in other words, and then of course there's a map from the ordinary theory of commutative rings to the ordinary theory of lambda rings. And then you pull back along that. So in fact, actually, what I'm proving is a little more than that the space change is a animated ring. I'm actually proving that the space change here is, the space change here is an animated lambda ring. So it's a simplicial, not simplicial commutative ring, but a simplicial commutative lambda ring, simplicial lambda ring. Right, so in particular, I also have Frobenius operations, which is maybe not entirely obvious. I have Frobenius lifts also on that in every degree. But I just didn't want to sort of, I mean, the reason I just sort of mentioned the consequence of that, which can be formulated without talking about lambda rings. And that is just this complete commutative thing. So everything relies on this computation of strict polynomial functors. And
Thanks.
that, as I said, imported from representation theory, work of Krause and others.
I have a question. This is Joachim.
Yeah, hi, Joachim.
So in the classical setting of, that's a big step from polynomial functions to analytic functions. But when you categorify, it seems that the step is not so big anymore. Like, because there's no problem with infinite sets or infinite dimensional vector spaces and so on. So this is exploited a lot in type theory and program semantics and things like that. So my question is if K-theory is also functorial in analytic functors.
No, I don't think so. I mean, for one, the notion of analytic functor in Goodwillie calculus is a little bit problematic. I guess, I mean, somehow this comes back to this discussion we had about how the two notions relate. And I find this a little bit, I mean, to be honest, I find this a little bit confusing in type theory, because somehow analytic is somehow a special case of polynomial.
Yes.
Right? And somehow good-Willi calculus, and like, I guess it's more like an ordinary analysis that polynomial is a special case of analytic. And so analytic means in good-Willi calculus that you're the limit of your decisive approximations. And of course you can ask for that. And I think then if you say it like that, then the answer is just no. K-theory is not polynomial in those. And the reason is that, I mean, if you think about it, what our theorem really does, and actually I should maybe have mentioned this earlier, somehow the ideas of how to extend, like if you have a polynomial functor from A to B, how to extend this to K naught. Right, the way I phrase this in terms of universal properties, but you can also try to work out explicit formulas. Right, so you want to know how to apply this to a formal difference. And somehow what being polynomial gives you is, it gives you like a finite formula for how to express direct sums in terms of the functor. Right, it's not like, I mean, it's not like saying the direct sum is f of m plus f of n, or f of m minus n is f of m minus f of n. But it gives you like a finite inductive formula for what f of m minus n should be. Right, that's what I sort of formulated in terms of these cross effects. So we can unfold that, for example, in the n equals 2 case. This is very instructive to unfold how this gives you a formula. But an analytic functor would be a little bit more problematic, because this would not give you like a finite formula. This would give you in some sense an infinite formula for what f of m minus f of n would be. And of course, we can't evaluate somehow infinite formulas on K-theory. I think that's why it's not the case. So maybe, I don't know, maybe in some fancy complete version of K-theory one could, but certainly not in like the naive possible way of K-theory.
Okay, thanks.
So if there are no more questions, we thank Thomas again for his talk. And we will resume in 8 minutes at 12:30.